So I'll digress a little bit and ask, what does it mean that two partons are color connected? I've used this simple textbook example of a quark and an antiquark, but that's not what we have in real collisions, right? We have at the LHC, even we have incoming color charges, and we have these showers, and we have quarks can branch to QQ bar pairs and stuff. So we've got complicated events with lots of partons in them. And sometimes they crisscross and stuff like that, right? So how do I know which partons are coming out of this should be confined with which other partons? Where should I draw these potentials? Between which partons should they form? And there's a complication, of course, that every single vertex in QCD includes this Gell-Mann matrix in color space that I probably also heard of. So tracing color correlations in general is quite a complicated problem. So at the end of the day, with, I don't know, dozens of partons or whatever, who ends up confined with whom? What the Monte Carlos do is they do a simplification. So we treat color flow in a simpler way, where we use what's called the leading color approximation to trace color correlations through all these part processes and showers. So what we base this on is just SUN, SU3 in this case, but it works for SUN, where we have fundamental representations, so triplets and anti-triplets, and there's the group product where the adjoint, the gluon color, 3 times 3 bar is an 8 plus a 1. And that means that in the limit that n is large, or actually n squared is large, we can approximate that we can write an adjoint as the direct product of a triplet and an anti-triplet. So we just use fundamental charges. A quark has a fundamental color index, an antiquark has an anti-fundamental index, and a gluon has both. And that's how we represent them in these event records. So we have these very simple rules for color flow. So if we've got a quark coming into that radiates a gluon, the gluon inherits the color, has a new anticolor, and then the quark carries that new anticolor. So it's very simple. It's a simplified representation of what the Gell-Mann matrices really do. And this is exactly also the structure that we would expect in gauge theory, that these charged gauge bosons repaint the quarks. That's what they do. Gluon breaks up, then the quark inherits its color, and the antiquark inherits its anticolor. It's very simple. For glue to glue vertices, there are 2, and we can select between them probabilistically how does the color flow in a glue to glue vertex. So this simplification allows you to trace the color flow. That's also the simplifications that color dipole and color antenna showers are based on exactly the same thing. It works up to 1 over NC squared. So since NC is 3, this is about a 10%. It's equivalent to the other sort of perturbative approximations that we make with alpha S is also of order 0.1. 1 over NC squared is order 0.1. So it is a useful expansion parameter, even though, of course, you'd like to do better, but dealing with the entire color flow is extremely difficult. So most of the work that we do is limited to this. So how does that look? If you look at an event record in Pythia, if you've ever done that, or in any event generator, you'll see these color tags. They're called Lezouche color tags. And so here I've just written the first stages of an event where in the leading color, so we're in this limit where the number of colors is large, and we're taking n formally to infinity. And so we've got a bag with infinitely many different colors in it, in principle. And so we just number them. And for some reason, we always start at 100 or 500 or whatever. So 101, 102, 103. Now there are only 3 colors in QCD, but we keep going. So the next one is 104 and so forth. And because each of these is unique and only shared by 2 partons at any given time, I always know exactly which partons belong in a dipole with each other, perturbative dipole with Coulomb fields, and it can radiate. And the non-perturbative dual of perturbative dipoles are string pieces. So I know exactly between which partons to form string pieces within the context of this approximation, because I can go and see which ones have matching color tags. This is a color, this is an anticolor. Okay, then there should be a dipole or a string piece between them. So that's just showing you how this actually works in the context of an event generator, if you look at that. And this is not specific to Pythia. This Lezouche color tag notation is used by all the generators. So, okay, so now we have a map where we can start changing the degrees of freedom. We need to get rid of these perturbative plane waves because they have to disappear. We need to get hadrons at some point, and at an intermediate stage, we're going to use strings. So we'll map quarks to string endpoints, and we'll map gluons in this way here to transverse kinks on strings. because they have a color tag and an anti-color tag. So they're a kink in color space. And so if we sort of look at the evolution of a system, then the string position will be moving like the gluon will be tracing out a kink on the string. So that's a very characteristic feature of the Lund string model, that gluon jets are described by exactly the same parameters as quark jets, but gluons have two string pieces attaching to them. So they lose energy twice as fast, they generate twice as many hadrons and so forth. So gluon jets will look different, but there are no new parameters introduced in the model to describe gluon jets. And then physics is in terms of this string world sheet evolving in space-time, and that has some fancy names in string theory, and it's exactly the same physics that we have here. It's just a sort of semi-classical physics in our context. But if you go to like an introductory book on string theory, you know, chapter 1 will have the Nambu-Goto action, that is the string action. This one is not great to quantize if you want to do actually quantum string theory. So there's a classically equivalent one, which is called the Polyakov action. That's the one they actually use. We typically talk about the Nambu-Goto action because, well, we don't really need it. It's such a simple system, and I'll get back to that. But anyway, these two actions are equivalent. So how do strings move? Well, we've got this constant tension on the string, 1 GeV per Fermi. So if I'm a quark escaping from, you know, I've been kicked from out of a hadron or something like that, and I've got, let's say, 10 GeV of kinetic energy, then this constant tension, I'm pulling out a string, and I have to deliver 1 GeV of energy to the string per Fermi that I'm traveling. So if I have 10 GeV of kinetic energy to start with, I can travel 10 Fermi. Before I have lost all my kinetic energy, and then I have to start moving back the other way. It's not quite a pendulum because it's not quadratic potential. It's just a linear thing. So for small kinetic energies, that's a very simple model of what the quark and antiquark in a meson are doing. In scalar meson, where there's no angular momentum, so they're not going around each other, they're just sitting there doing yo-yo. So that's called the yo-yo mode. Very simple model of mesons. And that looks like this. We've got an antiquark and a quark, and they're just, you know, sitting there building up a string. And then they have maximum kinetic energy, maximum potential energy, maximum kinetic energy. So it's a little bit like a pendulum, but again, with a linear potential. For larger kinetic energies, though, they're not going to do this little thing. I start building up a long string between them, and then there starts to be so much energy between them that this string can actually break, and I can create further hadrons. So pulling out the string more, there's a lower energy state, which is created by making new quarks and 2 hadrons instead. And nature will then choose the lower energy state. So this is formulated. I mean, you can see this kind of in configuration space. The actual model, the string fragmentation model, is formulated then in momentum space, just like perturbation theory. So we can think about field theory in configuration space. Maybe the first chapter of your quantum field theory, you know, notes or whatever is in configuration space, but then very quickly we go to momentum space. And the same is the case here. We want to map this model onto perturbative final states that come to us from perturbation theory in momentum space. We know the quarks and the gluons, what momenta they have. They're momentum eigenstates when we get them out of perturbation theory. So we use configuration space to kind of think about what's happening, the physical motion, but the actual model is formulated in momentum space.